Today we're going to take a look at section 3.2, which is called Rolle's theorem and the mean value theorem. In some ways, we could just call this the mean value theorem. All Rolle's theorem really is a very special case of the mean value theorem. So we'll talk about that after we've looked at both of them and explain what I mean by that. We are going to start with the special case, though, which is Rolle's theorem. All right, Rolle's theorem says to suppose that f is a continuous function on the interval AB, closed interval AB, and it's differentiable on the open interval AB, and the endpoints have the same y value, f of A equals f of B. And according to this theorem, that there is a number between A and B where the derivative is 0. Many times, pictures just explain it better than words, right? So that's what we're going to do. We're going to draw a picture with all these conditions holding true and see what that looks like and why the result has to follow. So go ahead and give yourself sort of an axis of some sort. And what you want is you want to have A and B. We've got A listed before B in the sort of setup, so we'll put it that way. And it says the y values should match. So let's just make them match here. So this is the f of A, which is also f of B. So these particular endpoints are at the same level as far as y value. What we know has to happen between them is that it has to be continuous, so you can't draw it without picking up your pencil, and it has to be differentiable. So differentiable means that it can't have some certain things happening. What are those certain things that can't happen? What did you think? What were you thinking? Sharp turns, asymptotes, jumps. Okay, so nothing like that can go on. Now, some of those we already ruled out because we said it was continuous, but the sharp turns didn't get ruled out, right? So this description actually rules out sharp turns. So whatever has to happen, it's got to do something like this or something like this, right? It's got to be smooth. That's differentiable, and it has to be continuous. You can make it as complicated as you want. You can make it as simple as you want. Probably your most simple one is to do something like this. Point being, there is some location between A and B where I have a derivative of 0. What does it visually look like to have a derivative of 0? The slope of what, Evan? Yeah, we usually think about it as the slope of the tangent line. If I were to draw a tangent line, I'd have the slope of the tangent line be 0, which means I'd have a horizontal tangent line, right? And can you see that happening on this graph? Something around right there. I have a slope of 0. Tangent line that is horizontal. This would be the location C. Now notice it doesn't say there has to be exactly one location. Now that picture I drew before where I had lots of turns going on, there had been lots of locations where I'd have a derivative of 0, right? So that's okay. This theorem just ensures that there's one. We know there's at least one place that this happens, and that place has to be between A and B. Now you could say, okay, but what if the graph didn't have any curvature at all? What if it looked like, say, this? Then what could we say? Yeah, everywhere it has a slope of 0, right? I mean, C is actually every point in between A and B, so that would be okay as well. The other one that I drew looked something like this, I think. This one clearly had several. In particular, it looked like it had about 3 points where it has these values of C. Okay, but we are assured to have at least one with the conditions that they're described to. Okay, so as we're taking a look at the next examples, our goal is to make sure that we have the conditions that have to happen. The 3 conditions are that it has to be continuous, differentiable, and the endpoints have to match. And we'll test all 3. Sometimes it will pass all 3. Sometimes it will fail at just one of them. Sometimes it will fail at several of them. If it fails at least one of those 3 conditions, then we do not know that Rolle's theorem is actually going to hold. We don't know that there's going to be a point that this actually works for. Okay? So, our first example, the directions say, determine whether Rolle's theorem can be applied. That means we have to check those three conditions. If it can be applied, find all values that work. All those values C where the derivative is 0. Okay, and then if not, we're going to explain why it can't be applied. So we actually, I know you're going to be doing this, and I checked it out because I was curious how WebAssign would do it. What it's going to do is it's going to give you like a multiple choice kind of thing where it's one of those, I had one of these tests when I was in high school where it's check all that apply. Yeah, so you really do have to check and make sure that each of the conditions either holds or doesn't. So we're going to make sure that we do that here as well. So the three conditions are what? Continuous. What's the next one? Differentiable. And the last one? Yes, f of a equals f of b. And on this one, the a and the b are 0 and 3. So we're going to test if f of 0 equals f of 3. Okay, is everybody good with that? These are the three conditions. We've got to check each one of them. Now, the first one, continuous. Why is this function continuous? Do you know? Okay, one at a time. Say, what did you say? There's no words undefined. What would it look like for it to be undefined? Okay, we might have a denominator with a variable in the denominator. What else might we have? Maybe a piecewise graph. This one's not defined piecewise. If we had a trig function, are there some trig functions that have asymptotes? Yeah, like tangent, that would be an example. Square roots we have to be a little bit careful with to make sure that it's defined on the interval we're really looking at. Obviously this isn't a square root, but we could also be careful about that one. So this one, what kind of function is this? It's a parabola, that's its graph. We call it a quadratic function, or more generally, it's sort of category functions. It's called polynomials. It's a polynomial function. Polynomial functions are always continuous. This one we almost get for free because it's a polynomial. It's polynomial, so this one's going to work. Cool thing, differentiable. It's the same deal. We get it because it's a polynomial. Now let's talk about the differentiable issues that could happen if it weren't a polynomial so that when we encounter them we'll know what's going on. All right, so let's deal with some of the issues that you guys mentioned. Let's do with the denominator one that Evan mentioned first. So if we have a denominator that's equal to 0, we actually have an asymptote. Clearly it's not continuous at that asymptote. Is it differentiable there? No. I mean, you have no chance of being differentiable if you're already discontinuous. Okay, you've got a continuity issue, you definitely have a differentiability issue. So we are definitely going to have those possibilities happening when we have denominators. If we had those vertical asymptotes happening with like trig functions, tangent, those kinds of things, same thing. Can't be, if it's not defined there, right? If it's not continuous there, it's not going to have a differentiable. It's not going to be differentiable there. Square roots are interesting. We're going to encounter that one very soon, actually. When you're dealing with square roots or cube roots, you have to be really careful because you can end up with some weird sharp turn kinds of things. So keep that in mind. If you aren't sure and you're dealing with something that's a square root or a cube root or something with a power that's the one we're going to deal with in a little bit here is going to have an exponential power that's going to be a fraction, which is the same thing as having cube roots or square roots kind of thing. Okay, take a graph, look at it. Look at it on the interval and check it out. Is it smooth or is it not? Okay, that will help you out on that one. All right, the last condition. So we get these two. Those are good. The last one is to check to make sure that f of 0 is equal to f of 3. So if I plug in 0 for this function, what do I get? It is 0. If I plug in 3, what do I get? It's actually 0 as well. So these two are equal, right? So do the conditions of Rolle's theorem hold? They do. We have all the conditions. So because we have these, Rolle's theorem will apply. Okay, so what does Rolle's theorem say? Well, it said that we can take the derivative And at some point between 0 and 3, the derivative will actually have a 0, right? It will have a horizontal tangent line. So if we take this derivative, what is f prime of x? Yeah, we mentioned this before we actually had our last test, that you're going to have, for the most part, cleaner derivatives. Now that you've learned how to take the complicated, messy derivatives, which, by the way, not all of you have come to see me to redo your skills quiz, right? Your gateway thing. I know some of you have, but not all of you have. So if you haven't done that yet, you need to get that done. All right, so I had said the deadline was going to be Friday, but since Friday's Good Friday, the deadline will be on Monday next week. Don't come on Monday next week and do it for the very first time. That would be a very bad idea, okay? So please make sure come in and redo that quiz. Take a look at the mistakes that you have made. Okay, so this is my derivative, negative 2x plus 3. And what this says is that the derivative at this value c, so if I put in the c in the place of the x, it will equal 0 somewhere, and I just need to solve this equation. And this is a simple linear equation. What value does this give me for c? Y'all know how to do this. What do you get? What was it? 3 halves. 3 halves? Okay. All right, 3 halves is what I have written down. Is 3 halves between 0 and 3? Yes, it is. Okay, so this is the value that Rolle's theorem said would happen, and we found it. Okay. Any questions on that one? It happens to be halfway in between. It doesn't always happen that way. Okay, this one happens to be that way, and it's because it's a parabola. That's kind of a unique feature because parabolas have this very symmetric property to them. All right, the next one's the one that I was alluding to in the last problem. Same directions. We have to check all these issues with continuity, differentiability, and f of b equals f of a. Okay? So, and we are going to check all of them. If one of them fails, we know we aren't going to do the second part of the problem. We're going to check every single part of the problem. So, is this continuous? This might be helpful for you to remember what this actually is. This is the cube root of x squared. That's what this is. And then minus 1 on the outside. That's what that 2/3 power means. All right. Is it, did I write it wrong? Are we okay? Cube root of x squared. Okay. Continuous. We're going to check differentiable. And we're going to check that f of negative 8 equals f of 8. Okay, let's just do continuous first. Continuous. Can I mean, if you want to, you can graph it, right? If you aren't sure what this looks like. Is it continuous? Yeah, it is continuous. This graph is continuous. Is it differentiable? Caleb graphed it. What's wrong with this graph, Caleb? It has a sharp turn. Where is the sharp turn? Yeah, it's at x equals 0. This is not differentiable. And I'll just sketch roughly the graph that you're seeing, that some of you are seeing, those of you who've looked at it already. It looks like this. It has a sharp turn at x equals 0.
So is there a way to know that without graphing it?
Is there a way to know that without graphing it? There really isn't a great way to know that without graphing it with the tools we've done so far. Yeah. Sort of being aware, because it has this weird look to it, it's not a polynomial. So knowing that you should take a look at it is something that, it should sort of be a red flag to you. That part of it should. This is an unusual kind of function. It's not the ones that we normally deal with kind of thing. This is not differentiable, okay? But we're also supposed to check the third condition. I mean, we know Rolle's theorem is not going to apply, but we're going to check and make sure that all the conditions apply. So let's check the third one as well. F of negative 8 equals f of 8. So if I put in negative 8 to this function, all right, and I'll do it from the cube root perspective. What is the cube root of negative 8? Negative 2. And negative 2 squared would be 4. Not negative, but positive, right? 4. And then 4 minus 1 is 3. Now, you're welcome to use your calculator to plug that in. I don't have a problem with that, but this one's pretty clean. We can actually do it in our head. I will ask you to tell why. See how it says if Rolle's theorem cannot be applied, explain why not? So like when I wrote this one differentiable, it's not differentiable at x equals 0, and this would be my justification as to why.
But because that works, we wouldn't need to do that.
Which one?
If they're
Oh, well, I'm not finished showing that it didn't work, but you're right. I mean, it does work, but you're right, it will. You're just going to confirm that both of them equal the same value by actually plugging in the numbers. Yeah. So kind of what I'm showing in red here would be your verification for it. So like if I put in now 8, oops, not negative, positive, let me do that one. So if you put in 8, Evan's right, this one actually equals 3 as well, and these two are equal to each other. Okay, so that's your confirmation. That's the show the work part kind of thing. Is that okay? So you're confirming it either works or it doesn't work. So this one, Rolle's theorem does not apply. Now, it doesn't necessarily mean there's not a value between them. There happens to not be one here. It just means that we don't know for sure that there is. You guys get the difference? No, because at 0, we have a place where it's not differentiable at all. So the derivative is certainly not 0 here. The derivative doesn't exist there at all. All right, let's try another one. Got to do some trig, right? Well, of course we do. Got to do some trig. Same directions. Checking to make sure that if it's continuous, differentiable, and if f of b equals f of a. So, continuous. What do you think? Yes. How do you know? Yeah, the sine graph is this nice smooth wave pattern, right? Yeah. Is it differentiable? Yeah, I used the word smooth already, didn't I? Yeah, this one's cool. We get these because it's the sine curve. Okay. Smooth function over here. We do need to check that f of 0 equals f of 2 pi. Whoops. All right, so then f of 0, what is the sine of 0? It is 0. And f of 2 pi, what is the sine of 2 pi? 0. Yep, these are equal. That was our third step to check. So what does that tell us? Yeah, it tells us that Rolle's theorem applies. Okay, so far so good. When Rolle's theorem applies, it did on the first problem, didn't on the second one. It will apply on this one. What's our next step? Take the derivative, right. So we're going to take the derivative. So what is the derivative of sine of x? Cosine of x. And Rolle's theorem says that this derivative has a value c between 0 and 2 pi for which the cosine of, in this case, c, not our best letter to use when we're dealing with trig functions, but we'll manage, equals 0. There is some location where the cosine of c between 0 and 2 pi equals 0. There's lots of places where the cosine value equals 0. We want to know the values between 0 and 2 pi. So what values, what angles satisfy this condition? Pi over 2, that's one of them. There's another one. And 3 pi over 2. There happen to be two c values for which this one works. Now, I didn't draw the graph of a trig function when I sketched my image initially, but we have this kind of thing going on with it, right? I showed you 3 locations. This one had 2 locations. Okay, you guys ready to take a look at the mean value theorem? So Rolle's theorem had 3 conditions: continuous, differentiable, and the endpoints match. right? The y values of the endpoints match. So take a look at the mean value theorem. Suppose that f is continuous on the interval, closed interval AB, differentiable in the open interval AB. Notice what condition isn't here. The endpoints, right? It doesn't say f of a equals f of b. All right, so as long as we're continuous and differentiable, this one says that there's going to be this weird location where f prime of c is equal to f of b minus f of a over b minus a. Now think with me for a moment. If f of a and f of b were the same thing, what would happen to this equation? It would be 0, wouldn't it? So all of this would end up saying, if f of b and f of a were the same, that f prime of c equals 0, which would be Rolle's theorem, wouldn't it? You take out that one condition, and you get this much broader description, but if I put that condition back in here, it still works. Okay? So Rolle's theorem is just a very special case where we have the endpoints that match. Now let me show you visually again what in the world is going on here, because this looks really funny, and it really isn't that funny. It really isn't that unusual of what it's describing. So what we're going to do is we are going to draw the f of b and the f of a at different heights so that we can see a different picture than we saw before. So we've got a listed, we'll list it first, and we have b second. And we're going to say that our graph does something like this. And there's no reason for it to have sort of this maximum point between the two. It doesn't have to. That's just how I drew it. Okay? As I've drawn it, is my graph continuous? Is it differentiable? Yeah. Okay, good. All right, so what in the world is this? Whoops. Right here. This right here. You've seen it before. What is f of b minus f of a over b minus a? It's what? It's the distance in the y values on top and the distance in the x values on bottom. It's slope. This is just a fancy way of saying the slope between a and f of a, right, that ordered pair, and b, f of b. It's the slope. So if I were to draw this line, I think that's pretty believable, and calculate its slope, that's what that quantity over here is saying. That's it. This fancy quantity over here is just saying the slope of that orange line. That's what the right-hand side says. What does the left-hand side say? Well, the left-hand side says that there's some location between A and B where I would have the same slope for the tangent line. So we'll see if I can make it believable. We'll go with that. Oops. If I draw it believably, this is what this is saying. Somewhere between A and B, I have a location C that would have the same slope as the slope that actually goes from A to B. That's all the mean value theorem says. Okay. This is the idea that if you went from your home, wherever it is you live, to the school, and you averaged a certain speed between those two locations, on average you drove 50 miles per hour, on average, okay? That at some point between here and your home, you actually really were going 50 miles per hour. Sometimes you were going faster, sometimes you were going slower, but some point between the two times, you really were going 50 miles per hour. And this has actually been used in courts of law without the people actually being able to know for sure and track that you actually were going over the speed limit at convicting people of speeding. Imagine if two cops were sitting up, set up a mile apart on the highway, and the first one clocks your speed and the second one clocks your speed, and you're not speeding. Well, how can they accuse you of speeding in between them? They can figure out how much time lapsed between when you passed one cop to when you passed the next one, right? They know it's a mile, and they can figure out what your average speed was. If your average speed's over the speed limit, well, at some point in between there, you were definitely going over the speed limit as well. Pretty cool, creative, mathematical kind of stuff, right? Tricky. All right, so let's see this one used. It's actually easier to verify the conditions of the mean value theorem because how many conditions are there? Two, just two. All we have to confirm is that it's continuous and differentiable. We don't have to check endpoints. Now, the other part of it ends up being a little messier because there's more to it. So let's check this out. Is this continuous and differentiable? Yes. We get this one, again, for free, kind of like we done the last one. This one, these check out because it's a polynomial. Okay, so what in the world does the mean value theorem say is going to happen then? Well, it says that I should be able to find f of b, which that would be f of 1, minus f of a, that's f of negative 2, over 1 minus negative 2. Okay, that's the slope between those 2 points. So we're going to calculate that. So what is f of 1? If I plug 1 in here, what do I get? 1. If I plug negative 2 in here, what do I get? Yeah, and so I have 1 minus 4, right? And then in the denominator, I have 3. Yes? So what is the slope I'm having happen here? It's negative 1. We get a slope of negative 1? Okay. All right, so we have a slope of negative 1. So when we're doing the derivative, instead of doing the derivative like we done the last one and setting it equal to 0, we're going to do the derivative and set it equal to the slope value. It's the only difference. So our derivative, what is our derivative of x squared? 2x. So we're going to take that derivative, evaluate it at c. So this would be 2c. And we're going to set it equal to the slope value we just calculated, which was negative 1. And what will c equal? Negative 1/2. Now, we do want to make sure that that actually occurs between the interval we're talking about, and it does. This one worked. Okay, is everybody good with that? Okay, let's take a look at another one. All right. 5 minus 4 over x. Our conditions are continuous and differentiable. What happens? And it's specifically on the interval negative 1 to 4. What happens, guys? Has an asymptote. Where does it have an asymptote? As x equals 0, right? Look at the equation, right? A 4 over x, I can't let x be 0. Is 0 between negative 1 and 4? Yes, this is a problem. So this has an asymptote at x equals 0. So this one would not apply. The mean value theorem does not apply. DNA, but not the DNA in your body, okay? Does not apply. I'm going to make a change to this, though, so that we can continue to do the problem so you can see what would happen if it did apply. The issue here is that the interval included 0, right? Yeah? So let's just pretend that the problem had started off slightly differently. Same problem. So what's my function? 5 minus 4 over x. I'm just going to change the problem because I want to do the problem like you would see it happen. Because I want you to see another mean value theorem when done. And let's do the interval from 1 to 4. If I had the interval 1 to 4, would I be okay? Yeah, I would. This one would be fine. So this one, continuous, differentiable, we're good to go, right? This is continuous and differentiable on this interval, 1, 4. So I'm not saying on all your problems you need to change intervals. That's not the point here. I just want you to see the problem done one more time. Okay, another problem with mean value theorem. Okay, so 1 to 4. So we're going to find the slope between the x values of 4 and 1. So f of 4 minus f of 1 over 4 minus 1. All right, so if I plug the number 4 into here, 5 minus 4 over 4, what do I get? I get 5 minus 4, which would be, 5 minus 1, which would be 4. That's what you told me. Yes. How about if I plug the number 1 in? Yeah, I would get 5 minus 1. Did I say it right? 5 minus 4, which would be 1. Is that what you have, Josh? That's what you're telling me, right? Good deal. And then we have 4 minus 1 in the denominator. So what's 4 minus 1 over 4 minus 1? We actually get a slope of 1. Okay, nothing special about 1s and negative 1s. They just happen to work out this way. Alrighty then. So what we're able to do then, let me move this over a little bit, is we know that we should be able to take the derivative of this function. Now this is not especially written in a way that I like. I would rather have it written, say, like this to do the derivative, right? 5 minus 4 x to the negative 1. Okay, the derivative of 5 is 0. What's the derivative of negative 4x to the negative 1? 4x to the negative 2. And if I rewrite that, that would be 4 over x squared, right? So far, so good? This says that I should be able to take the derivative at the value c. So this is 4 over c squared. And it should equal the slope value that I found before, which is 1. So this is 4 is equal to c squared. Technically, c has 2 values it could be. What are the 2 values? 2 and negative 2. But the c value that we are looking for is which one? Positive 2. Why? It's the only one on our interval. And I wanted you guys to see that sometimes you're going to get answers that are going to be outside of your interval. So make sure that you're reporting only the answer that's in between the interval, or in the interval that you're looking at. So this is c is equal to 2. Again, I changed the problem by changing the interval so you could see another problem, okay? Any questions on this one? All right.